see. Do you want to switch that, Leslie? Okay, so there we go. Thank you for attending today's talk. I'm very excited to introduce today's speaker, who has joined us from a location south of the border and will present the next great Cascadia earthquake. How did we get here? But first, I have a few announcements. The next presentation will be on March 18th, and this will be David Williams, and he will be discussing secrets of Seattle's geology, connections of the human story and the geology story. This will be our first hybrid Zoom and in-person speaker or talk. And then on April 29th, Sky Cooley will be presenting soil climate evidence for timing of the Cascade uplift and creation of its rain shadow. This will be Zoom and in person. And then on May 13th, Vince Matthews will present Global Scramble for Natural Resources. This is a Zoom only presentation. Remember to check out our webpage for the presentation specifics, like the in-person locations. There will be 2 coming up, and they're at 2 different venues. So please check the website. Now the introduction. It is a great honor to introduce today's speaker. I first became aware of Chris's work in the late 1990s while I was working on my master's thesis on the west coast of the Olympic Peninsula. I have since heard Chris present at GSA and am amazed at the data that we get from the offshore turbidites. My husband, Jeff Tepper, previously brought Chris to the University of Puget Sound for a colloquium, and one of our sons thought the talk was pretty cool, although he didn't think it was cool enough to divert him from a degree in forestry. Our speaker says he grew up in a science household. He was fortunate to have a NASA contract engineer for a father. Chris mentioned something about an Apollo mission, and maybe he'll have something more to say about that later. Chris says it was never a question on whether or not he would study science. He grew up in California, and he found his original passion for geology in high school. But in college, Chris looked at all the sciences and thought geology was the rogue science. He said geology is kind of off the books. You just do it. As a biologist, you cut up frogs. As a chemist, you blow things up. But as a geologist, you just load up the field rig and go to Death Valley. Chris obtained his undergraduate degrees from Humboldt State in 1980. He received a BA in geology and a BS in geologic oceanography. In 1990, he received a master's in structural geology from Oregon State University. And in 1994, he received a PhD also from OSU. After graduating OSU, Chris continued as a professor teaching in the College of Earth and Ocean and Atmospheric Sciences, where he never had to worry about student motivation. He found his teaching to be a great public service because students would go and spread the word about earthquakes. Part of his teaching assignment required that he teach an earthquake course for undergraduates, kind of a Rocks for Jocks science class. And he loved it because those students' jaws would drop when they would learn about the risks where they live. And some of them had just recently chose to move to OSU or to Corvallis. Chris has great stories to share about earthquakes, including being in a meeting and earthquakes happen throughout the whole week. I'll let him tell the story because this experience made him more optimistic about a magnitude 9 earthquake. Recently, Chris retired and is now an emeritus faculty member at OSU. He and his wife sold their home, and during the last 5 years with a couple of friends had outfitted a 50-foot sailboat. He and his wife are currently in Mexico, La Paz, Mexico, with sights on continuing to sail to the South Pacific. Chris says that the ton of new cores he received in August can be worked on from anywhere. Chris describes himself as a marine geologist and geophysicist with a focus on great earthquakes and structure of plate boundary fault zones around the world. He is well published and is a great speaker. And what many folks don't know about Chris is that he loves windsurfing and acrobatic flying. When I pressed him about the flying, he said, yes, it includes daredevil flying, and he has been doing it for 16 years. Hopefully he'll share a little bit more about that towards the end. Currently, the plane is pickled for the next 2 or so years. please help me welcome Chris Goldfinger. Thank you, Chris.
Hi, Carol. Thanks, Carol, for your two kind words. And hi, everybody. Thanks for taking some time on a Saturday afternoon. Hopefully, it's nice where you are. But if not, uh, we'll have a good time talking about earthquakes. So I want to say this is mostly a geology talk and not so much a seismic hazard talk. You know, what to do about earthquakes and all that. I want to focus on the paleoseismic evidence for Cascadia great earthquakes. And we'll get my slideshow going. Okay, so first of all, just want to acknowledge 30 years of collaborators. This is only the top few that are listed here, but they're probably in close to 100, something like that, of collaborators, students, ship's crews, and folks that have made all this possible. And you're only going to see the tip of the iceberg. So thanks to all of them. And so Cascadia earthquakes, how did we get here? It's been instead of a long, strange trip, it's been a short, strange trip, actually. And maybe a subtitle for this talk would be Subaqueous Paleoseismology in Cascadia and Elsewhere. Why does this unlikely method seem to work? So that's sort of woven throughout this. But we'll include, both marine and land data. I'll be talking mostly, though, about the marine. So if you haven't seen this scene in the Big Bang Theory, Sheldon, who studies mostly esoteric astrophysical things like string theory and things like that, thinks geology is the Kardashians of science. And the funny thing is that I kind of agree with him. We're all geologists or interested in geology, but you got to admit geology is way behind the other sciences for whatever, the reasons are unclear, but we're catching up. Plate tectonics is pretty new, and we've got a lot of catching up to do. So just to put that in perspective, Armstrong and Aldrin were on the moon 53 years ago. Is that the right number? Yeah, I think so. And hippity hopping around on the moon, doing arguably the most advanced thing that humans had ever done. And but at this time in history, plate tectonics was only 6 years old. 1969. It was really only accepted in 1964 after the Alaskan earthquake. And so just imagine that. You can fly to the moon, but we didn't know, where mountains and volcanoes came from before that time. The explanations were sort of crazy, like the stork brought it, types of explanations. And so, in that context, we're still learning big things and still making big mistakes in a science that's, effectively almost brand new. And there's Buzz Aldrin setting up a seismometer of all things on the moon. And the seismogram at the bottom is the lunar module impact from Apollo 12, the next mission that landed. So coming back to Earth, here's Cascadia with the water drained out and offshore bathymetry. And it's a little ironic that Cascadia played a role in the development of plate tectonics and seafloor, the new science of seafloor spreading in the early 60s. And that's a fun story to tell that would take an hour all by itself. But the bottom line is the magnetic stripes on the newly formed Juan de Fuca plate and Gorda plates played a role in demonstrating that seafloor spreading existed and that the crust went to zero age at the mid-ocean ridges like here, and then got older symmetrically, going in both directions. And so it was only a very short time from when that paper came out in 1961 until the 64 earthquake in Alaska. And during that time, plate tectonics was swallowed hook, line, and sinker and became very much accepted everywhere around the world except Russia, which was kind of an interesting thing. But anyway, so at that moment, the scientists of the world were just stunned and zoomed around the world trying to looking at all the fault systems, the subduction zones, and the big crustal fault systems to see how they fit this hypothesis. And one by one, it was shown that it fits perfectly, it fits perfectly, it fits perfectly. And the exceptions were few and far between. And as people zoomed around doing this, they completely forgot about Cascadia. And, as we all know, sometimes when a data point doesn't quite fit, you maybe tippy-toe around it for a while and then come back to it later. Do the easier stuff first and come back. That's what I do. And so it took 20 years for people to come back to Cascadia and say, well, wait a minute, there's something wrong with Cascadia. It sort of looks like a subduction zone with the poor geophysics they had at the time. The seafloor magnetic data seemed to fit the model, but there was just one problem. Cascadia did not have the big dipping plane of earthquakes that it should have, that all other subduction zones have. And so people thought, well, okay, we'll come back to that. And maybe a few suggestions were thrown out there that maybe it's aseismic because there's tons of sediment subducting there, and maybe it's wet and well lubricated or something like that. But nobody really published that explanation, and there are plenty of other subduction zones around the world that have those same conditions. And so that didn't fly very well. And then another thing that was floated just informally, that maybe the subduction here had stopped, and because GPS hadn't been invented yet and couldn't measure it, the resolution of the seafloor magnetics was only about 500,000 years ago. So you could 500,000 years. So you could conceivably stop subduction here and not resolve it for 500,000 years. But then Mount St. Helens went off in 1980 and reminded everybody pretty graphically that this thing was active. And of course there were other eruptions of Mount Lassen and other volcanoes in Cascadia. So that idea didn't fly either for lots of good reasons. And whoops. Oh, can I hide these buttons here? Hang on. There we go. Okay, so we had two possible explanations. And those of you who know this music know what's coming. Here it comes. It's coming around on the guitar. So there was a third possibility that nobody had counted upon, and that was that Cascadia was a fully locked and loaded subduction zone that just hadn't had an earthquake in recorded history. And that idea was floated in the early 80s by Tom Heaton, and an article was published in 1984 showing the Seattle Space Needle, and suggesting, what if Cascadia is really like Alaska and Chile, which had these M9 earthquakes in recent years. And it was a pretty provocative idea and frightening one as well. And then a few other things happened. So in the late 80s, Brian Atwater began to work on the coastal stratigraphy, and I'm sure you've all known this story for a long time. And this was 1987, and of course he had to work on it a little bit before that. And the famous stratigraphy of peat, and then sand bed, and then bay mud, and then modern marsh on top, he proposed was the effect of a 300-year-old earthquake that had subsided the marsh, leaving this peat behind, overtopped by a tsunami. And then since the subsidence was of about a meter or so, was semi-permanent, it was in the bay. And so we had bay mud here. And through the seismic cycle, it gradually came back up and was recolonized with a modern marsh. And a number of us were students back in those days, and I remember sitting at a picnic table at Willapa Bay, thinking, this guy is crazy. There must be 100 ways you can explain this. And then we talked about it and batted around a bit, and as it did in the science community, and it had a very short path to the fact that there actually wasn't another good explanation for this at all. And so Brian did an amazing job pulling this story together out of nowhere. Nobody had observed this and written about it in the scientific literature about a real time, historical event. And then in 1993, Kenji Satake found the orphan tsunami deposit in Japan. And I think most people know that story about the arrival of a wave in Japan. That the data from those written records were turned into tsunami models that tested all of the subduction zones around the Pacific, and Cascadia was the best fit. And so that's how we know that the last Cascadia earthquake was January 26, 1700, about 9 p.m. So kind of an amazing triumph of sleuthing, especially considering that plate tectonics was so young. We're figuring out these details of a past earthquake down to the time of day. Was a remarkable piece of work. But let's flash back just a moment, just a little bit earlier. Just after plate tectonics was accepted, the early oceanographers at Oregon State and at UW were out there, and these were sedimentologists taking cores offshore and just trying to figure out some very basic things about sediment transport out in Cascadia Basin. And these are the names of the folks, a couple of UW folks and 4 or 5 there were a few more, but from OSU. And these were not folks that were looking at grand theories or plate tectonics. They were all sedimentologists looking at sediment transport. Peripherally, they were also, of course, working in this proposed new concept of a subduction zone. And they were well aware of that, but they were mostly sedimentologists and keeping the blinders on a little bit, looking at these deposits that they found out there. So they mapped channel systems as best they could with the very crude electronics they had of the day, and they mapped sediment transport paths off the continental margin into the deep sea. And so they wrote up their theses. All of these students. Vern Kalm here wasn't a student; he was the mentor, the advisor for all the OSU students. And they wrote up their theses, and subduction and earthquakes were never mentioned in any of them. They were simply lots and lots of tables of heavy mineral analyses and grain size and things like that, and very detailed descriptions of their cores. And that was the end of it, really, until John Adams came along. And this actually predates Atwater by just a little bit. And he wrote an abstract for AGU in 1985 proposing that the turbidites that were found out there, which are submarine landslide deposits, came almost exclusively from great earthquakes. And he was the first to have proposed field evidence representing these earthquakes. And here's a slide out of his paper. The paper came out in 1990, but the abstract was 1985. And showing his hypothesis. And what he reasoned was that all of these cores, almost all of them, contained the Mazama ash from the explosion of Mount Mazama, now Crater Lake. And it was 7,600 years ago, roughly. And so all of these cores contained it, and John simply counted the number of turbidites up above the Mazama ash and found that 13 was a popular number that could be identified in almost all of these cores. It wasn't perfect. There was a little bit of noise. There was 14 in one and 15 in another, but it was very close. And so his first aha moment was, well, what are the chances since you have a number of mechanisms that can generate turbidity currents in the deep sea, what are the chances that you'd have the same number in a given time period over this broad of an area, 1,000 kilometers roughly? And he felt that the chances were near zero that would happen. You should have random numbers controlled by various sources. And then he also noticed that 2 of the main channel systems, Willapa channel, which is right here. Hope you can see my cursor. I made it bigger, Carol. So, and then Juan de Fuca channel, which is up here and comes down parallel to the deformation front. And both of these channel systems come to a confluence right here. And so Adams noticed not only did you have the 13 turbidites in all these cores, but these cores on one side of the confluence and on the other side had the same number. And then below the confluence, you could go down here 150 kilometers or so, and down here 200 kilometers or so, and there were still 13. So a much brighter light bulb went on, and John proposed that, well, there were really only two explanations for this. One is that uh, one channel system randomly had 13, the other channel randomly had 13. And then at the confluence, then you would have 26 events, and that through attrition for distance, from the distance, that you would have to lose 13 and to wind up with this coincidental 13 number. And that didn't seem very likely to him, so he proposed that what actually happened was that these things all arrived synchronously, and synchronously here means within minutes to hours, not the usual geologic sense of synchronicity, more like a human scale synchronicity, and that they arrived at the confluence at the same time. The turbidity currents then merged and went downstream, leaving 13 deposits just as they had upstream. And to me, this is one of the simplest and yet most brilliant little thought experiments that I know of. So John Adams never went to sea. He never physically went to UW or OSU and look at these cores. He never did any radiocarbon ages. He just drew this figure at his desk. And so I'll just leave that hanging for just a moment, and we'll move on. So now one of those students I should mention is Hans Nelson. He's my longtime collaborator, and he started working on this project in 1996, long before I did. And so I met Hans at a meeting one time, and he said, "Have you read this paper by John Adams?" And I said, "Yeah, I read it." And at the time, I was more doing geophysics and structural geology, and he said, "What did you think of it?" And I said, "Well, seemed pretty good." And he goes, "Well, I did my thesis on the Astoria fan, which is right here." And he goes, I don't buy it. Those are all my cores. That's all my data. And I'm just not buying it." He said, "I think there are only 3 Holocene turbidites on the Astoria fan." And Hans Nelson was Mr. Astoria fan. He discovered the Mazama ash, had a science paper on it. And so he was the most credible guy on the planet on this topic. So he convinced me that Adams was probably wrong in some way. And so we talked about it, had a lot of beer, and decided to write a proposal to NSF to go out and test this hypothesis in a more modern way. And so we did. So we went out in 1999, our first cruise. There have been, I think, 5 or 6 of them since then. And we collected all these cores in gray, and the white ones were the original cores from the 60s that Adams had used. And so cores last a pretty long time in a refrigerator, but these cores from the 60s were starting to lose it and desiccate and whatnot. So more cores were needed. So we went out and collected all of those. And here's the ship we used, the RV Melville, with Scripps, best big ship at the time. And we started at, somebody's got some feedback. So we went out and we left Astoria. That was where the port was, and we went out and started collecting cores in Astoria Canyon and Astoria Fan, where Hans had been talking about. Then we moved up to the Washington Canyons and so forth, and we started working our way southward. And about the middle of this cruise, traditionally on these ships, we have a presentation for the ship's crew. They work really hard, and they're not seeing the science. They're not getting the thrills out of it that we are. So we give them a nice presentation so they can see what their hard work is going into. And so halfway through the cruise, we pulled all the cores out, laid them out on a table, and Hans and I got together and talked about what we were going to say to these folks. And so what happened was, once we had laid the cores out, and Hans and I looked at them all, and we kind of assessed where we stood in this thing and what we were going to tell the engineering folks. Right at that moment, we realized that we were wrong and Adams was right. And everywhere we went, we found the Mazama ash with 13 turbidites on top of it. And we found the reason that Hans' original thesis data did not jive perfectly. It was just a matter of core site selection that made the difference. And so we did a 180 right there during the cruise. And so when the ship's crew gathered in the library for this talk, we told them that Adams was right, and we were collecting more and more evidence to demonstrate and test this hypothesis, but it looked like it was working. And one of the chief engineer of the Melville came up, and he goes, it's because I've been working on this boat for 25 years, and when you guys give us a science talk, it's just gone in one ear and out the other, over the top, and because I can't understand what they're talking about. He goes, but I can count to 13, and I totally get what you guys were talking about, and that was pretty cool. And so we had this it actually works moment, and so in the coming year or two, we were kind of befuddled by our failure to disprove Adams, and we became reluctant paleoseismologists, which was never in the plan at all. And so this is some of the story of how all that turned out. So in order to do this, a really important thing was to have a good map of Cascadia, and that didn't exist. In the 60s, they'd drawn it by hand from soundings and had this fundamentally correct but map that was just far below the resolution that was needed. And the problem was for us that Oregon and Washington bathymetry data were classified by the Navy at the time, and you couldn't just go out and collect new data, and they wouldn't give us theirs. And so we had to resort to some odd things. We had to hand, kind of like the 60s guys. For Washington, we had to hand digitize soundings, aided by the regional Gloria side scan data, which was a survey that Ronald Reagan initiated in the 80s. And so all of that time and continuing on up through present day, building a good map of Cascadia was and continues to be a big part of this story. And so in Adams' hypothesis, here's what a little bit more modern view of that might look like. And the idea was you generate synchronous turbidity currents across 1,000 kilometers, and this would be like a day and a half's travel time for those turbidity currents. Long pathways up in the north and much shorter ones down in the south. And what that does is it builds up, here's what one of the cores actually looks like in just a regular photograph, these sort of railroad track turbidites in here. The dark units are the sandy layers. And it turns out that these sandy silty layers make up most of the core, more like 95% of the core, and the hundreds of years between them only are a few centimeters apiece. So this is a very long and detailed record of these submarine deposits. And so we had to start to learn how to become submarine paleoseismologists. This is a field that, other than Adams' paper and one in the Mediterranean, essentially didn't exist. But the basis for doing it is much the same as things are on land. So we mapped channel systems, and we learned about how the depositional sequences were laid down. Here's this Astoria channel. Here's a point bar, and we found out that cores on the lee sides of point bars were very good sites. They were not so erosional as the main thalweg of the channel, and would usually recover a very nice complete record. And so we're learning how to do subduction zone scale operations, but it has to come down to almost outcrop scale to get sites that work well. And also in a more modern sense, we're now using modern technology to help with the cores. So back in the 1960s, they had basic core description, which was a sheet of paper and a pencil. And you just describe everything you can. You feel the grain size. You maybe measure the grain size using settling velocities and things like that. It was very, very crude. Their descriptions from the 60s were excellent, but it sort of ended there. There just wasn't anything more to it. And so now we can put cores in what's called a multi-sensor logger, and we can get density, resistivity, and a lot of other physical properties out of the core, magnetic susceptibility and so forth, out of these cores. And we can kind of run them in a production mode, sort of like a factory ship, and do this all in a van at sea. So we walk away from a cruise with a really complete record of the cores, including the hand descriptions as from the 60s. And then we split the cores and we take them to another lab and get them CT scanned as well. So we have resolutions from 1 to 30 microns or so, and so it's almost like way too much information about these cores. And so I'll just take a pause here to jump ahead and think a little bit about what does it get you to work in the marine environment? When you do paleoseismology on land, you can walk up to the fault oftentimes. You can touch the fault. You can dig trenches across it. You can do all sorts of things that you can't do underwater. So being underwater has its limits. You're on a ship 3 kilometers above. The resolution of the imaging you can do isn't as high as you want it to be. So you would think that being in the marine environment would be a disadvantage for paleoseismology. And in some ways it is. You can't do certain things at the kind of resolution that a land geologist can do. On the other hand, land geology or land paleoseismology has radiocarbon data being at the core. It's the most important thing often, besides the interpretation of a trench, the trench details, but it's radiocarbon based. But in the marine environment, you actually have some advantages. This is what your toolbox looks like. You have other short-lived isotopes. You can build age depth models as the sediment is raining down. Relative dating tests like the confluence test we just talked about. Historical events and so forth. Those things you can get on land sometimes. You can track individual beds with sub-bottom geophysical profiles. You can use industry methods that are very well developed, well log and lithostratigraphic correlations that you'll see some examples of. Derivative parameter tracking of things like bed thickness and mass per event. We have geochemical tracers that you can detect with heavy minerals and XRF. You can hydrodynamically model the flow paths of turbidity currents. And then side scan sonar and bathymetry helps also map the flow paths. So actually, what seems like it might be a disadvantage, to me, it seems like the toolbox is actually very rich. And so let's talk a minute about the methodologies. So basically to go beyond atoms and think about a big fault system holistically, there's a laundry list of things that could generate submarine landslides and turbidity currents. And here's the list here. So storm and tsunami wave loading, sediment loading, just sediment piling up and failing on its own, storm or hyperpycnal discharges, bolide impacts, so that's a big one. Not very common, but it's out there. Then we have great earthquakes, we have crustal earthquakes, we have tectonic oversteepening of parts of the subduction zone that lead to failure, and we have gas hydrate destabilization. So there's frozen methane gas out there that can melt and destabilize a slope. So with this laundry list, then, how could you distinguish between all of these things or any of these things in order to get an earthquake record? We only care about one of the things on this list. And it turns out it's a lot easier than you might think. And there's 2 basic paths. There's first principle sedimentology, and then there's the method that Adams used, which is demonstrating areal extent and synchronicity of deposits. And sedimentology these are not either or, this is a complementary set. Sedimentology is not as commonly used. It's a little more difficult to go at a deposit from first principles and say, oh, this was caused by an earthquake. It can be done, and it has been done, but I'm going to talk mostly about the second one because this is just it's what we've done, and in my mind anyway, it's a little more effective. So if your tool is synchronicity and areal extent, let's just take a look at what happens to this laundry list when you consider that. So if you have correlation over a distance of 1,000 kilometers, and Cascadia is kind of a small subduction zone. It could go, other larger subduction zones, this works even better. But if you have 1,000 kilometer correlation, now let's just say that correlation is certain in this case, then what can you do to this list? Well, you can knock out gas hydrate destabilization because these are local random sorts of things. that aren't expected to go those big distances. And the same is true of sediment loading. That's going to be a local effect, but not a regional one. The same with crustal earthquakes, and the same with tectonic oversteepening. So now we've got and storm and tsunami wave loading. That's the one thing that might conceivably stretch over 1,000 kilometers, but it would have to be a storm, beyond what we even know Cascadia to have these days. So in a relatively short examination of this list, if you have the correlation, you can shorten the list quite a bit. And storm hyperpycnal discharge is also mostly not local, but it's not fully regional either. And that leaves you with bolide impacts and great earthquakes are really the best ways to get regional synchronous triggering of turbidity currents. And bolide impacts, they happen. We know about Chicxulub and all of that, but they're relatively infrequent. And so we can consider that along the way when we can compare it to other evidence. And so it's a relatively short path to get to great earthquakes, despite the fact that you've got this long list. And so over the years, just take a pause to show, this is a list of where these methods are being applied today or have been applied recently. And it's grown from leaps and bounds, from a handful of people working on this to now hundreds of people working on it in all sorts of different contexts, from major IODP drilling cruises to small lake investigations around the world. And so it worked for us pretty well, and it seems to be working for others pretty well as well. Okay, so how do you actually do it? What do you actually do? Well, we go out and collect core samples using a piston core and a ship. And the core samples come up in 4-inch sprinkler pipe, and they look kind of like this picture on the left. This is one of them. This dark material is the sand and silt. This other dark material is the mud on top, the tail of the turbidite. And this light material with the pink indicator here is the hemipelagic sediment. That is the background sedimentation offshore. It's partly comes from the land, it's partly biologic from the ocean. And so this is material that's deposited at a very slow but very, very even rate. So it's actually sort of like a clock ticking, and measuring its thickness tells you something about time. And then here's the turbidite below that. And this blotchy stuff in the middle here is bioturbation. And that's one of our enemies that makes it more difficult to get timing of things accurately. So what we do is we take out a centimeter or two of this sediment just below the event bed of interest, and here's the base of that bed. And we pick it apart with doing microscope work to pull out 400 to 500 of these foraminifera. These are grain size or sand grain size little critters. Takes a few hundred of them to get a decent radiocarbon age, and then we determine the age for that sample. And to get even a little more geeky, here's a 2 centimeter slice taken out of that, and we radiocarbon date that. The age gives us roughly the midpoint of this sample, but that's not the age we want. We want the age of the event bed up here. So we subtract off the time represented by this to get up to the base of that. And that's what the equation is down here. And so this gives us a Z depth in the core of the event bed, and we can use that to either get a single age from it, or later on we're going to build age models that use the sedimentation rate to help refine the ages a bit, to try to get as close as we can to the actual age of that event. And of course, with every bit of science, there are always lots of complications. And one of the complications we deal with in radiocarbon in the ocean is that when you date something on land, that thing was alive and breathing and using atmospheric air. And that calibration curve is pretty well known. There's a calibration curve that goes with radiocarbon in the air. In the ocean, though, it's not very well known. We only know what that calibration difference is for the 20th century, for example, and we don't really know yet very well how much it varies in time, because the critters in the ocean, they're not breathing the air, they're breathing oxygen that's in the water, and the water is old. It hasn't been in contact with the air for a while, And so there's an offset in time of a few hundred years. And so without going into too much about this geeky detail, part of this all was based on building a time and space variant reservoir model for the Northeast Pacific Ocean. And that's really kind of required to proceed further into getting ages of earthquakes. And so we built one. It's sort of the Mark 1.0 version. It needs a lot of work. But it seemed to be a pretty good start for a first version. So now let's say you come along and you do those methods and you have, say, 20 turbidites in a core, and you date them all, and you have some reason to believe, as John Adams did, that certain events seem to correlate over big distances, either just by counting from the top or looking at their radiocarbon ages. So now Adams' work didn't include radiocarbon, but ours does, and so we can look at some of the beds that Adams proposed were synchronous over big spaces and look at their actual ages. And so these panels are 6 examples of that, where we took the radiocarbon ages from all of these different sites up and down Cascadia, the different colors here, and we just stacked them on top of each other to see how well the ages matched up. And so, of course, radiocarbon has big uncertainties. You can get the age of something, but its uncertainty is plus or minus 150 or 200 years. So that's a problem. So we're in the world of statistics of small numbers. If we can't pin it down exactly, how permissive of a good fit is it, or how bad of a fit is it? And that's sort of the world we're in. And so these are just 6 examples out of about 35 of what that looks like. So this is calendar years across the bottom, and this is the plots of these ages stacked on top of each other. And then on top of that is the gray plot is what happens if you statistically combine all of these ages to get a single age to represent this bed. And so that doesn't mean that, that the fact that you do that doesn't mean that they're actual, that it's really the same bed and they're coeval, but this is a test of permissiveness of that. Is it plausible? And so it turns out it is pretty plausible, and I'll show you some more statistics about that. And all of the beds that were combined in this way and regionally correlated pass some statistical tests that, weak as they are, they're at least in agreement. And so it's important to realize that the coevality or equal age of event A and event B just can't ever be proven with radiocarbon. No matter what you do, what statistics you throw at it, you just can't ever get there from here. So it's good to keep that in mind as we go along. So here are the statistical tests, and this is probably the maximum geek level of this talk, and I apologize for the stats. But for those of you who are interested at this level, I just wanted to include a couple slides like this. So this is the statistics from a radiocarbon program called OxCal that lets you do what we just showed, that is compare ages head for head and see how well they fit. And so the orange bars are the minimum statistic of a good fit, and the light and dark blue bars are the actual data for the 25 or 30 something or so. My slide's cut off. Events that we tested. So taller bars are good. So all of these events pass this first statistical test pretty well. The second one is a chi-squared test, where the chi-squared value is the light blue down here, and the red and blue bars are the 95% and 99% confidence interval. In this case, also taller bars are better, and so the so-called null hypothesis that their ages being from the same distribution is not rejected. So the data would suggest that these correlations, just as Adams had surmised, they work pretty well with the statistics, and that's about as far as you can go with statistics. There's nothing much else you could throw at it. But actually there is. So you can look at other derivative parameters. So this is bed thickness. So if you think about this gigantic continental margin shaking and all these landslides forming and all that, you would think, and I would think, that all the beds that were deposited would be all different thicknesses. There would be no connection whatsoever between one site and another. a site that doesn't have much sediment supply versus a site that does, why should they be the same? Well, it turns out, and this is a plot of bed thickness by site, that they are very much the same, and that should not happen. And if it does happen, it means, to me anyway, that there's some connection between these sites. That's not just, random deposition of beds. And so you can see the plot and the stack plot, that there is a loose connection between these sites, and you'll see this some more of this, that bed number 11 and bed number 16 are giants in the record everywhere you go. So it turns out what this is saying is that big ones are big everywhere, small ones are small everywhere, and the medium ones are all medium, but they're not, they're a little more equivocal. And so that's something that should not happen unless the driver is an earthquake, and the series of earthquakes or varies by size. Here's another one, another derivative parameter, mass per event. So this is the mass of material determined by gamma density delivered with each event. And again, you see there's quite a pattern. The big ones are big, the small ones are small, and the mediums scatter a bit. But that's another derivative parameter that should not track, and yet it does. And so here's just a bigger, so now this is inter-event time. So the radiocarbon, the median radiocarbon age of each pair of events, the inter-event time is plotted here. And you can see these track very well. So even though we're dealing with radiocarbon and its big uncertainties, when you look at the whole series of the Holocene as a pattern down core, you see these things track pretty well. And there's some exceptions, exception there and exception there. But overall, the pattern is quite good. And this gap here of 1,000 years really stands out, and this gap here of another 1,000 years also stands out. And these 2,000-year gaps are two of the tools that help tie this record together from site to site to site. So now what we're trying to do is build a picture of, did Adams' hypothesis really hold up or not when we compare it at this level? And so to see that, to see something about this a little more graphically, I'll show you an example of what bed thickness looks like. The simplest possible parameter. There's no interpretation here whatsoever, just the thickness of the bed. And so if we take and mark the bed thickness in a black bar for some of the cores, and these cores are next to each other, shown here, are spanning about 300 kilometers of the margin from central Oregon down to southern Oregon. So a pretty big distance. And now let's take all the raw data away to just look at the bars, and then let's stick them closer together to make them easier to look at. And you get, oh my God, it's a barcode. Look at that. It is kind of unbelievable. And it's not perfect. You can see this bed here doesn't extend that far north, and this bed here doesn't either. There's variability to it, but it's kind of, to me, it's kind of stunning to see geology reduced to a simple barcode like this. And so now let's take zoom out and look at the whole margin. So this is Canada, essentially Canada on the left and southern Oregon on the right, and play the same game. So now we've taken the entire Holocene, and the only manipulation of the data here is to stretch it out so that 0 time is at the top and 10,000 years is at the bottom, and the cores are somewhat different lengths, but we have those two time datums pretty well. So we're just going to make time 0 at the top, time beginning of the Holocene at the bottom, and then just look at this. And when you first look at it, it doesn't impress you as a particularly good match. I don't think. It doesn't for me anyway. But then we'll do one thing to it. We'll just make all of the bottoms of each of these beds line up, and this is a test of the assumption that they're synchronous in time. So let's make them all line up and then look at it. Oh, wait a minute. There is something, there is a pattern here. So here's the 1,000-year gap that I talked about here, and here's the second 1,000-year gap. And so now this is starting to look a lot more like a barcode. And this exercise is called flattening in the oil industry. So we've just assumed that time is, that the vertical scale is time, and that these beds all occurred at the same time as a hypothesis, and just to see how well it works. And if we flatten it at the bed tops as well, it gets a bit better. And then we can add the radiocarbon timescale now on the right and take a look at it. And it looks once again like a barcode. So this is how, all of this years of radiocarbon dating and examining these beds can be reduced to some fairly simple graphics with very little manipulation. And so, so now, what other things can we throw at this to see, how well the atom story holds up? So let's look at some of the individual beds, since we can zoom in on these individual beds down to the micron level with CT. Let's just see what happens when we do that. So when we collect the physical property data, this is what we see, and this is actually these are older X-ray images. You'll see some better ones in a minute. But here's the descriptive diagram, the kind of thing that they would have had in the 60s, which we still do. It's an important part of this. And then here are the geophysical wiggles from that MST core scanner. So here's the light blue is density, the red is P-wave velocity. Over here is the dark blue is magnetic susceptibility, and over here in the purple is grain size. And so right away you can see, and the same with the panel on the other side. So right away you can see that this turbidite has three sandy sequences in it that you can see here, 1, 2, 3. And each one of those makes a kick in the geophysics, like here in the density particularly, and you can see it here as well. And what that means is that these, the density and the magnetics and most of the geophysics are acting as proxies for grain size. So the sandy parts contain magnetite, and magnetite makes both the density and the magnetics kick. And so that's a great help, because doing grain size on hundreds of meters of core would take, the whole science party until they were on oxygen walking and walkers. It's almost impossible to even conceive of that. So here we have a grain size proxy, and you can run these cores in a few minutes and get detailed information about the turbidites. And here's how detailed. So we're down at the micron or tens of micron levels, and you can see things like a silty lining of a burrow of a critter crawling through the mud here. You can see, really far more than you need for paleoseismology, which is great. So finally we have a tool that has more resolution than we actually need. And now compare this to the 1960s guys that were with it, pencil and paper. It's just this is like turning the lights on and seeing everything. And so this technique was borrowed from the oil industry. They call it well log correlation. They don't have cores in the oil industry. They just drill wells and they log the cores with geophysical tools. And this is sort of what they look like, and this is what they use to correlate cores or drill holes from site to site. And of course, they're looking at different physical properties. They're looking for oil, and they want to see if they've drilled a well over here and it's a winner. They want to see if they can track that same deposit, which are turbidites usually, to another site and drill another winner somewhere else. And so this technique's now 101 years old. It was invented by Schlumberger in 1920. And of course they just had paper records, and now we have much better tools to play with these things. But it's essentially unchanged since that time. So let's take a look at what happens if you have the core. We have a big advantage over the oil industry. We have the cores, and we can go back to them as many times as we want. We can get age control with radiocarbon. We can do all these things that they can't do in the industry. So let's take a look at 250 kilometer span of cores, and we'll just zoom in on this a little bit so you can just see what it looks like at the level that we look at it. And the idea here is this is done visually. This is not done by signal processing or something like that. This is like a guy with a clipboard standing in a trench and interpreting it. This is geology. But take a look at the geophysical wiggles and the cores and the CT images for these two cores, and see if they look to you like they're kind of similar. These are the radiocarbon ages on the left for one core, and radiocarbon ages on the right for the other one. And so I hope they look similar to you. They look similar to me anyway. Here's T11. Here's our biggest event in Cascadia. Here it is in the other core. And you start to see sequences. So for example, this large unit followed by two small ones, followed by the giant. That sequence is repeated over here as well. Giant, two small ones, this one, and then, or big, two small ones, and then the giant. And you can look at these sequences and subsequences, and after staring at these data for a while, you begin to realize that this is the same sequence. And the radiocarbon ages matched within the statistical limits of radiocarbon quite well. Oops. Okay. So here's just a few more examples of that. These two panels, by the way, the last two cores were 250 kilometers apart. And the way, I'll just digress for just a second, the way we discovered that you could correlate over this sort of a big distance was a pure accident. And almost everything we learned along the way in this project was a pure accident. We weren't able to disprove Adams' hypothesis, and then this well log correlation business came about when I was correlating cores that were right next to each other. So a piston and trigger pair, which are collected a meter apart every time we deploy our rig, and I was just correlating those routinely, just to help, deal with the geologic variability over short distances. And I found two cores that correlated well, and I was working on in the far south of Cascadia. And then I realized that one of the two cores was the wrong file name, and I looked at it and went, "Oh, that's the wrong core. Dang!" So I took it out. I put the correct one in, but it wasn't the wrong core. It was the right core, and it turns out they weren't 1 meter apart. They were 22 kilometers apart. And I just kind of went, "Really? These things look identical, and they're 20 kilometers apart." So I got the next core down the same channel system. Now we're 100 kilometers away, and it looked just as good. And so this is Friday night before AGU, and I completely redid my whole talk. I started talking about core correlation. But anyway, so this was discovered that this actually works by accident, and we were just very lucky that it happened. So this is 3 panels just showing pairs of cores in various places in Cascadia. The middle one was taken from the previous diagram. This is Hydrate Ridge, Central Oregon, and Rogue Channel in Southern Oregon. And you can just take a look. This little more colorful version of it is a little easier to look at, and just look at the sequence, and you can see that it's very much the same with some differences. One difference is the Mazama ash, which appears prominently in this core in T14 down here, appears only very weakly in Hydrate Ridge, and that's because Hydrate Ridge has no possible delivery path of the Mazama ash. So the Mazama ash failed to appear in exactly the place it shouldn't have appeared, which is a really nice test of this whole thing. And so Rogue Channel has the possibility of storm inputs and other inputs that were on that laundry list of 8 things. And Hydrate Ridge does not. It's completely isolated. It can't receive any terrestrial input, and yet the records are nearly identical. So this is a nice way to sort of work out from a golden spike special isolated place to other sites around the margin and see how they compare, to see if storms really do play a role. And they apparently don't for a number of reasons. And so the same thing can be said of the other panels here, and I'll just move along for the sake of time. Okay, so here's another example of that, showing some of the prominent big events here. So T11, our famous big guy, 5,900 years old. It's big in every single core system. And T16 is the other giant, also appears big in every single core in all the different systems. And so at this point in time, we started to realize that if this relationship, the big ones are big, the small ones are small, is real as it apparently is in the data, for quite a few years we had no way to explain this. Why would that be true? How could that possibly work? And much like Atwater's original hypothesis, the last man standing really was that it's the earthquake that's controlling these things directly. It's not sediment supply, it's not the transport paths, it's not any of those things, because they're consistent along 1,000 kilometers of margin. So the last man standing is the earthquake. So we concluded that these big deposits are coming from bigger earthquakes and wrote a paper about it called Superquakes and Supercycles. And so this is something that shouldn't work, but does. And it doesn't work everywhere. We tried it in Sumatra, and it doesn't work there very well at all, with a very different kind of lithology. And so this is the kind of thing where if it works, great. If it doesn't work, it's just a tool in the toolbox that doesn't apply. And so, so let me just show you one more example of this. So these are the density trace wiggles from 4 cores. And what these represent, again, is a proxy for grain size. So we don't really care about what the real density is or the real magnetic susceptibility. These are just proxies for grain size. And so what we see is 2 fining upward sequences sitting on top of each other, making the density increase for each one. And you wind up with a sort of molar tooth looking kind of a thing. But each one of these has 2 peaks, so and so, like this. There's some variability, and you might, and you wouldn't say that these are identical, but they have a self-similarity. Now, if you look at these in context, here they are. These span 700 kilometers from northern Washington all the way down to Rogue Canyon. So to us, this is the gift that keeps on giving, that helps make this Cascadia stuff possible. We're not, by any means brilliant geologists. We just got very, very lucky, and this correlation is so simple that I had a 6th grader do it with colored pencils once, and he did it exactly the way we do it. So this is very simple stuff. So I've been mostly talking about the big ones. Sometimes sandwiched between the big ones are some smaller ones. This one labeled T2A is a thinner, finer grained turbidite. You can see it there in the CT scan pretty clearly. But it's not as big and robust as its margin-wide neighbors, and it also doesn't correlate along the whole margin. I showed an example of one bed or a couple of beds that didn't correlate the full length, and this is what they look like in CT. So, so these beds typically are found mostly in southern Cascadia. Most of them are gone by the time you get to the Astoria Canyon. Many of them die out in mid-Oregon. So if these are earthquakes as well, then they represent probably smaller earthquakes limited to southern Cascadia. But the criteria for determining these as earthquakes are not as robust as the big ones. They don't have all of you can't use all the tools in the toolbox on these. So they're a little more speculative in that sense. But they do have the main features, and they do have the grain size kicks and the geophysical kicks. And here's just for the super geeks, a set of smear slides from one of these events showing the lithic percent as you go up toward the center and base of this event, and then and so on. So they have all the characteristics. They're typically bioturbated more. These big events tend to kill all the infauna. Where the little ones don't, they bring down sort of a pizza party and the worms go crazy, and they tend to chew up these things and making them more difficult to recognize. So one interesting thing that's come to light recently is that this not only works offshore, it works in lakes as well. And so here's an example from, on the left, these traces are from Triangle Lake, just west of Eugene, and roughly at a similar latitude, Hydrate Ridge, Central Oregon. And so if you just take a look at this black trace here, which is the magnetic susceptibility of these events in Triangle Lake, and then compare it to the offshore core, you can see they're almost identical. And the radiocarbon event age of this event is almost identical to the offshore, and so on. So the idea that the earthquake might be driving some of the fundamentals, like how much material is released in each of these events, if true, it should extend to lakes as well, and I would argue that it does. So the quality of the correlations, there's some range from great to terrible, and so I won't belabor this, but we have a subjective sort of quality scheme here, and here's just the description of what goes into that. and what went into the published papers. So they're not all perfect, they're not even all great, but there are enough good ones to tie the stratigraphy together, we think. And so here's what our working diagram actually looks like in Washington. I've been showing you small vignettes of it. Don't worry, we're not going to zoom in on little bits of this. This is just way too much. But what I want to show you then is the modern version of the confluence test. So these are the northwestern systems of that confluence. The ones on the right in the blue box are the south and eastern systems. And so let's take a look at what more we can do with this really cool confluence test that Adams did. So here's what the actual bathymetry looks like today with the channel systems in green. And we can take a look at the fact, so there's the original confluence there, but it turns out when you have good resolution data, it turns out that there are actually 6 more confluences out there and one actually below. And so to pass Adams' original test, it has to pass all of these tests, really. If it fails any one of these, then the record at the downstream confluence shouldn't match. And it turns out to get down to the level of understanding of these channel systems, we're using side scan sonar, for example, to look at Juan de Fuca channel. And this dark blob here is mud, and the light patch here is sand. And so we're looking at the frontal thrust of Cascadia, which is this ridge here. And as it grows, it blocks the channel, and mud piles up behind it just as it would anywhere else. It's just a river system, essentially. And so understanding the channel and the current turbidity current distribution at this level is helping understanding, differences in the record and so forth. And exploring alternative models. This is an alternative model that Brian Atwater proposed a few years ago, having the turbidity currents run essentially over the top of the accretionary wedge to short circuit the confluence test. We tested that, and I'll show you the outcome of that in a minute. Well, not in a minute, I'll show it to you right now. So here's a hydrodynamic model of turbidity currents coming down Quinault Canyon. And this is a model that's taken from an inversion of the actual core data. So it's not just a hypothetical model at all. And so it shows that turbidity currents coming down Quinault Canyon make a sharp southward turn along the Quinault Channel, and that they just don't really have the power to go over the top of these mountains, the accretionary wedge. So that was one of our tests of the alternative hypothesis. And we've used hydrodynamic models to test Adams' original hypothesis. And so here's right down here is the original main confluence. Let's just make this go a little faster. And there was a bit of a problem in that the travel time is quite different if you assume that the turbidity currents stop at the canyon heads, or start at the canyon heads and travel this distance. The distance is quite a bit longer on the north side than it is the south side, but it turns out that that problem is mitigated by the fact that the frontal thrust is also failing in providing turbidity current material at the frontal thrust, which makes the travel time distance wind up being about the same. So when we come back to Adams' hypothesis, each of these core sites now is showing a pair of numbers, and it's the number of Holocene turbidity currents and the number of post-Mazama turbidity currents. And so you'll see numbers like 19, 13, 20, 16, 20, 13. There's quite a bit of consistency of this. There's a little bit of noise in it, just as Adams originally found, and some exceptions to it that are shown in red. But it turns out the exceptions all have some physical reason for their existence. And so the white ones are the highest quality renditions of this, and it turns out it's just about as consistent as Adams' original story. And then we can throw yet another thing at it. We can do heavy minerals. And luckily, the heavy mineral analyses were done by the UW and OSU students, bringing them back into the picture from the 1960s. They did a lot of excellent work, which is, there's so much of it, it'd be very, very difficult to reproduce today. And but we don't have to. It's all done. And fortunately, UW and OSU used the exact same method, so we don't have to compare apples and oranges. And so, so let's take a look at that. And what we find is a heavy mineral suite with clinopyroxene and hornblende ratio of less than 1 up here, and glaucophane coming from the Fraser River source up north. Down here coming from the Columbia River, we have clinopyroxene and hornblende ratios that are much bigger, greater than 1.3. No glaucophane whatsoever coming out of the Columbia River basalts. And then, so let's take a look at what the samples look like along these two paths. And what we find is the northern source here with the green checks, and the southern source without glaucophane in the red X's here. And let's see, and I forgot to mention, when you go downstream, where they should mix, they do mix, and you get ratios that represent a nice mixing of this heavy mineral suite and just trace glaucophane. So as far as I can see, this is about you know, the best test that we can think of, and somebody else will think of more, I'm sure. And Adam's desktop diagram seems to pass with flying colors, which just still to this day blows me away. So it's always nice in science when another group comes along and does something completely independently that happens to corroborate what you've done previously. And this is Hamilton et al. In the Canadian Journal of Earth Sciences, and a group of Canadian Geological Survey folks went out and sampled a place called the Slipstream Slide off Vancouver Island, a ways north of our northernmost sites. And I won't go into this in great detail, but here's the Slipstream Slide shown on this map. Here's our northernmost site at Barkley Canyon, excuse me. And so they did basically the same thing we did. They built an age model and they correlated these two together between Slipstream and northern Cascadia from our data, and found a good correlation between the two. And just lastly in this, we've been working in lakes as well after we found these nice potentially correlative deposits in Triangle Lake. We've been working on more lakes, and so this is some of you folks that are on the Olympic Peninsula. This is Leland Lake and Lake Sawyer that's over in Kent, Washington, correlated across the Puget Sound. And these deposits were once thought to be potentially forest fire deposits. Looks to us more like they're probably earthquake deposits that can be correlated across Puget Sound. And I won't, in the interest of time, I won't say any more about that. So, so this horrendous diagram, paleoseismologists call a space-time diagram. And don't worry about it, but I'll explain what it is. So this is all the radiocarbon data in Cascadia. The blue stuff is all the marine sites. The brown, these symbols here, are all the land sites. So I mentioned Brian Atwater's work, but of course there's scores of people that are working in every marsh up and down Cascadia for decades now, and all their data is on this diagram. And so what we've tried to do is assume the minimum number of earthquakes that would satisfy all of these data reasonably well. And so that's the green bars here. And the dark green lines are the correlations, the well-logged correlations between core sites, and the green bars are the best fitting age that would fit an earthquake that would satisfy that data. So this is an interpretive diagram. Of course, we can't demonstrate with great certainty that any of these things are actually earthquakes, but the consistency is pretty remarkable. And so this is what we proposed as the earthquake sequence. But and here's just what that looks like in more detail. So this is Cascadia has sort of gone from the worst known subduction zone in the world to the best known subduction zone in the world in terms of earthquakes in a relatively short time. It's become a sort of petri dish for developing new methods to get out a subduction zone that isn't making earthquakes. And so the seismologists don't have much to do in Cascadia. At OSU, our lead seismologist works mostly in Nepal. There's really very little for him to do in our own backyard. So, but there's a way more fun way to look at these data. So if we know if we think we know the timing of the earthquakes and we think we know the along strike extent roughly, we can look at making a movie, basically, slide frames of the Holocene earthquakes. And so that's what this is going to be, Cascadia, the movie. So this is going to play at about 200 years a second, starting at the beginning of the Holocene, and go forward in time. So the colored dots represent the sites where this event is thought to be observed. And so in the beginning of in the early Holocene, you'll see mostly blue dots offshore, and only a few land sites that are lakes appearing. And we'll go forward in time. We're at about 7,500 years ago. There's T11, the biggest event, 5,900 years ago. And so you'll see a diversity of rupture types here, at least lengthwise. Some small ones down in the south, medium-sized ones that end in somewhere in central Oregon, and then full-length ones like this that clearly correlate the full length. And now at about 3,000 years, you start to see many more land sites recording these data. So the land record is about between 3,000 and 4,000 years old typically. And with paleoseismology, of course, if you've got marine and land records that you can compare head to head, that makes the story that much better. So now we're down to 800 years ago, 500 years ago, and then what we call T1, the famous 1700 earthquake from January 26th. And of course, we have the orphan tsunami evidence from that, and you almost all certainly know about the Battle of Thunderbird and Whale. And so it was, my version of this story is the Native Americans who knew about this all along. The geologists took a long time to figure it out, but the Native Americans said, why didn't you just ask us? We knew about that. Of course, their version of the story, the Battle of Thunderbird and Whale, is quite different than our version. But when you read the original stories, it sounds a lot like a great earthquake and tsunami. And of course, theirs has a parable in it. Don't build your villages too close to the coast in case this happens again. And so here's the summary of those. That was 46 events in that movie. There were 19 of them that are thought to be more or less full length. 2 or 3 more that stop a little bit short, somewhere in offshore Washington. This group stops somewhere near the Columbia River, and there are big uncertainties to this, so don't take this too literally. A couple more stop in Central Oregon. Quite a few stop at Cape Blanco, and that is reasonably well constrained by tsunami modeling at Bradley Lake. A few more, actually quite a few more that are further south their origins are much less certain. And only a single event that we can ascribe to a northern patch rupture. How are we doing on time, Carol? Where did we start?
Well, we're almost at 5:30, and so I'm not sure how much more you've got to present. Is there?
Well, let me just show a few things, and I'll wrap it up. We can just have some discussion then.
Okay, thank you.
Okay, so of course, this is one of my favorite earthquake jokes. Of course, we all live in subduction zones, and everybody wants to know. And even though this isn't a hazard talk, we all either live here or recently did live in Cascadia, and so the probabilities of earthquakes are always, something that's always going to be on at the forefront. And so, luckily, in Cascadia, we have enough data now between the land and the marine paleoseismology. We don't have to rely on a model, on a recurrence model and forecast of earthquakes that comes from small number statistics. We actually have the data. And so if we plot all the data for, let's just separate this into two chunks. We'll call it the northern margin and the southern margin. And we take the 20 or so events in the northern margin. And these are these blue dots are the recurrence intervals between those events. And if we take a look out into the future 50 or so years and put a target there, we can see that most of the event intervals, this is time increasing on the bottom, most of those event intervals are beyond the time of interest. So they're more than 360 years from the last event, and many of them are 400 or 500, even up to 1,000 years between events. And we've only passed a few of these intervals at the present time. So putting that into numbers, though, so that means we only have about a 14% chance of one of these events in the next 50 years. And so the number from our data matches the numbers from the land data and what's in the USGS national maps very well. But it's just statistics. It's not, we could still have one tomorrow. Where things are different is if you gang together things and call them southern margin, and we do the same thing. We go out 50 years into the future and plot all the recurrence times from the southern margin. Now you can see that to the left of this target, to the left is the past, and to the right is the future. We've gone past almost all of them already. And so there are only 1, 2, 3, 4, 5, 6 events that have longer recurrence times than the 300, in this case, we'll call it 360 years of our target. And so the average repeat time in southern Cascadia, including all of the events of all sizes, not just the M9s, is more like 240 years. So we're 323 years into a 240-year cycle. So we're actually well past the expected mean time for that. But again, it's still just statistics of small numbers. And so that's where this number, people sometimes wonder, why do we hear different probability numbers for Cascadia? And it's because it's spatial. The north and the south are not the same. And the south is sitting at around 37% with a big error bar, of course, where the north is sitting at 14%. And unfortunately, there was an article in the New Yorker, which is a great article, but they kind of convolved all this together and made it seem as if Seattle had a 37% chance of a great earthquake, which it doesn't. So they made one kind of major standout error in a otherwise pretty good article. So one of the other neat questions we can ask is, so how evenly spread out in time are these events? And the simple answer is they're not at all. So this is, again, the 19 big ones, and they're pretty clearly clustered. There are 5 events here. Here's the 1700 event here in a cluster of 5 with a 1,000-year gap. Here's another cluster of 5 and another 1,000-year gap. And then the clustering gets a little fuzzier back in the first half of the Holocene. So less certain about that. But they're not evenly spread out in time. And this is what makes people who work on recurrence models and statistical probability, it makes smoke come out their ears, because there's no current model that can deal with this. And so currently in the national seismic hazard maps and in policies and whatnot, this kind of possibility is not dealt with at all. And so we assume that there's some sort of a distribution rather than a clustering like this. But you can see that it makes a big difference. If this cluster doesn't continue as its predecessors didn't, we could be looking at a 1,000-year gap as the next sequence. On the other hand, if it has one more left in it, that could be coming up soon. So the recurrence probabilities go from something like 5% to something like 40%, depending on whether you're in a gap or not in a gap, or in a cluster or not in a cluster. And so, and these clusters are repeated in the land data. The land data cuts off about here, but this 1,000-year gap in these 2 clusters are well represented in the land data. So it's not just the turbidites showing this. And Alan Nelson and Harvey Kelsey noticed this in their 2005 paper. So this is pretty well known, and it's a big deal. If this is really being driven by something and it's not random, then in a cluster or not in a cluster is a big deal. So Okay, so this is where I should probably stop because I was hoping I'd get far enough to tell another little tale, but I should probably stop here. And
Well, Chris, I know you've got oodles of data and so much knowledge,
I'll
and
just
um, and I do appreciate your time, especially with Carnival going on just a few feet away
oh,
from you.
no
Thanks for
worries.
giving up your time. We do have some questions that are coming in to the chat, so if that's okay with you, I'll go ahead and start.
Sure.
I have to
Yeah.
scroll back. Let's see. Let's see. Oh, here's the first. The first one is actually a comment from a friend, Gary, over on Woodby Island. And let me just see. Um, it says, "We love outer space. We spend 10 times as much as studying the ocean we depend upon. I'd rather see a butterfly than go to outer space." That was David Attenborough.
Yeah,
Quote from
yeah.
him, I'm assuming.
But the thing is,
Um,
we can do both. And but it's true that we're spending a lot of money flying helicopters around Mars, and I love that stuff too. But we're not putting the effort into the world and the oceans that we need to. I'd have to agree.
yes. Well, Jeff Tepper really likes the historical approach to the story. Let's see. Sorry, there's a lot in the chat.
Chris, if you could turn off your screen sharing, we can
Oh,
see more of you.
oh yeah, okay. Here we go.
Let's see. Looks like there was a question answered. A nostalgic reminder of my core logging days. Let's see.
In terms of core logging, I can just make a quick comment that when I have oil industry people walk by posters and see presentations that I do, they always go, "Oh, this looks great. I can see that correlation from across the room." But my land geologist colleagues who are not, or at least sometimes not familiar with these methods, they look at it and they look at me like I'm some sort of an insect, and they go, "What are you talking about?" But anyway, people who've done this before, um, and particularly people in the industry, uh, seem to be pretty happy with it.
Okay, next question. Reading how Mr. Goldfinger or Dr. Goldfinger's team collected the turbidites, I learned they were on 1,000 to 3,000 meter water depth, which is reported to be a seismic and tsunami geographic area. Would the co-stakeholders agree this is an appropriate geographical area for a long-term buoyant subduction zone research center?
Oh yeah, yeah. I mean, the Japanese are doing it. Japanese have cabled observatories offshore, and it does a whole bunch of things for you. It tells you what the subduction zone is doing in real time. You can have an Ethernet cable, and you can log into it and see how it's moving, how it's breathing, and how it's doing all sorts of things. We currently have a very static view of the subduction zone that comes from past geologic evidence, um, but long-term and real-time monitoring is totally possible, and it'll happen. There are proposals out there now that they work on for a while, and then sometimes they die. But there's some new ones coming along, and sooner or later we'll have them. Canada actually has one right now that's in operation.
Great, thanks. Okay, next one. Chris, what have geologists learned from, oops, oh bother, I just scrolled too fast. What have geologists learned from the recent earthquakes in Turkey? I think those are more shallow than, but I'll let
Yeah,
you answer.
well, Turkey's a shallow crustal earthquake. Those faults at the triple junction there are more like the equivalent to the San Andreas. Um, what they'll learn from that, hard to say at this point. It's more of I don't think there's going to be necessarily a fundamental turning point in understanding of those fault systems or triple junctions or strike slip faults. What we're really learning is that the building codes around the world just can't stand up to those kinds of earthquakes, whether they're in Turkey or the Pacific Northwest. And
Right. Okay, the next question is there any indication that the basic subduction origin of our earthquakes may evolve over time into something more like the strike slip nature of the more gentle San Andreas earthquakes?
maybe they're referring to so Cascadia is sort of undergoing a transformation. That the San Andreas is moving, and the triple junction is moving northward. So Cascadia is getting smaller, and the whole region is being transformed from a strike slip, from a subduction margin to a strike slip margin as the San Andreas gets longer and Cascadia gets shorter. And so eventually it's the fate of Cascadia to become a San Andreas extension, basically. It's going to take a while, but I'm not sure if that was the meaning of the question, but
I think it might have been. Okay, so Jeff is actually asking, have your studies led to new ideas or understanding about turbidity currents in general?
oh well, let me just put up one slide to answer that question, and reshare it. So, whoops. Let's go back. So my answer to that question would be yes. And the reason is this: the part I couldn't that I trimmed out that I would have loved to talk about is that as sedimentologists, we're all taught that the layering of a turbidity current comes from the hydrodynamics as the current flows down the canyon systems and over hill and over dale, and that's what's controlling the sediment, the grain size sequencing in the turbidity current. And the assumption there is that the earthquake source, or the source of the turbidity current, plays no role in that it's all hydrodynamics as you go down the hill. And that model works pretty well for passive margins, where failures are typically more or less pinpoints on the upper slope somewhere in a canyon head somewhere, and where you would expect hydrodynamics to control the outcome. But most sedimentologists are trained in this, and I was, this is how it works, the BOMA sequence and all of that. But it turns out that the source signature of the earthquake, remember I was talking about the big ones are big everywhere and the small ones are small everywhere. And it turns out there's a hypothesis out there that we proposed that the source signature of the earthquake is actually embedded in the turbidite bed itself, and that stacking sequencing comes from heterogeneous earthquakes that are applying a longitudinal structure to a current. Then these earthquakes take 4, 5, 6 minutes to evolve, and so there's plenty of time for them to input a structure to the turbidity current, and that gets spit out at the bottom of the hill as a vertical stack. And so to answer Jeff's question, I would say that on active margins, you have the hydrodynamics that you had before, but you may be superimposing a source signature of the earthquake on top of that's controlling the actual deposit. And this is something that many sedimentologists hate. This is probably the most controversial thing about all of this. But it's really not. It's really just a difference between how you're trained and what type of margins you've been working on versus most sedimentologists have not really been working on active margins. And most studies of turbidity currents and turbidites come from passive margins where the oil industry works. And so it's just a difference of where people are working and where they're not working. But so this is how I would answer Jeff's question.
Okay, thank you. It looks like Larry would like to do let's do part 2. So that means we need to invite you back. Let's see. Chris is saying that was fabulous. Thank you. Gary is replying. Thanks for your excellent presentation. Safe travels. William is asking, Chris, what factors led to your retirement? Were your peers at OSU surprised by your exit? Okay, so I guess we want some gossip.
No, not really. I just, I'm 60. I just turned 67, And I just
Congratulations.
thank you, I made it this far. And some of the things I wanted to do, like traveling and whatnot, just had a requirement of being physically able to do those things. So you know, I have to say it's hard because I'm still in the middle of doing this work and I still love it, but you only get one go around in life. So I'm going to keep working, but do it with carnival and palm trees in the background some of the time anyway.
Well, yes, as soon as you're done here.
Right.
Bruce Bjornstead said, excellent. Rose, thanks for the presentation. You actually made statistics fascinating. And let's
Thanks,
okay,
Bruce.
Jeff. Okay, Jeff also wants to know why you chose Lake Sawyer for coring. I think there's another, Carl Wegman is next year going to go over and do some coring over there too. So
Yeah.
I think it's at Lake Sawyer, but
Our choice was based on which lakes could we go to that were controlled by counties where they didn't need federal permissions to work there, which meant archaeological, studies and all sorts of things. We worked in lakes where you could walk up to a county manager and say, "Hey, could we take a core in your lake?" And they go, "Oh, sure, no problem." And that was, and that's literally what controlled it. We had a grant running, and we just ran into a buzzsaw of federal regulations to say work in the Olympics and other places, and we didn't have the resources to even to follow through on all the process that they wanted. So the lakes were chosen not geologically, but on a permission basis. And it's a very long story, but that turned out to be a really good thing. Lake Sawyer and Lake Leland, for example, are just great examples. And it's a fun long story, but that was the reason.
okay, it looks like Celine. Thank you for bringing this knowledge to the surface. Cascadia must prepare for the big one, one way or another. This must impact decisions for offshore wind and the ban of offshore drilling. John says, thank you. Tom Badger says, glad this is recorded. Need more time to absorb the excellent illustrations and data presentations. Great work and great talk. Thank you. Gary says, we're going to have to build hovering cities on land and floating cities on the coast. Heidi says, thank you for the excellent presentation and fascinating data. Heidi Temco, retired geologist, Auburn, California, Port Angeles, Washington. Gary, how much of this turbidity sediments is coming from tsunamis?
Oh, that's a good question. I think the short answer is not very much because we're working in 3,000 meters for the most part. And what they found in Tohoku, for example, was that there was a tsunami backwash deposit that came out across the shelf and mantled the upper slope. But by about 1,000 meters, it sort of faded out and went to a very thin background. And I think that's what's happening in Cascadia. I haven't done the work. In the way they demonstrated that in Tohoku was because they had very short lifespan isotopes that came out of the Fukushima power plant. And that was terrible, of course, but they were useful geologically. We don't have a tool like that to test that, but we can look at sites like Hydrate Ridge, the site that's very, very isolated and can't get any input from the outside because I didn't show the picture of it, but it's ringed by mountains, basically. It can't get any terrestrial input. And so its stratigraphy correlates so well to the other sites where that's not nearly as certain that I think the tsunami is probably not playing much of a role. But that's pretty subjective, and I'm not that sure of it.
Well, thank you. And Gary says, as a non-geologist, I want to say thanks for this fascinating presentation. I learned a lot of great new words and concepts. Now to find someplace to use them to impress my friends. Okay, oops. Chip fellow HSU undergrad from '94, really appreciated your presentation. Thank you, Tom. Can we get a virtual tour of your sailboat? That's a good one. Nels, any relationship between Cascadia subduction zone and Columbia platform basalt flows?
Oh, that's a good question. I'm not the expert on that at all. I don't think so. I mean, Columbia Plateau basalts and all that are, as my understanding is, they're related to the North America running over the Yellowstone hotspot. And at some point in the past, that had to have passed through the subduction zone, essentially. But the interaction of that and how that works, I think that's still, I think understanding that still lies in the future.
Okay, and then Joe, as the last comment, this was truly a delicious presentation. Thanks much. And yes,
Thanks,
Chris,
Joe.
thank you very much for your time and energy and all of the knowledge and doing all the public speaking that you do. Thank you. Cheers. Okay,
All right.
so we'll be
Thanks, everyone.
posting this talk soon. Cheryl wants to know, do the glacial megafloods show up?
Yes, they do. Thanks for that question. That's a great place to find it. So yeah.
Thank you, Cheryl.
So we just went out on a cruise in just this past August, 2022, and so our coring equipment has improved a bit, and so we typically used to take 30-foot, 40-foot cores. We're now taking 50 and 60 footers, and we can now reach the Missoula flood deposits pretty easily. And so the Holocene earthquake sequence is sitting right on top of the Missoula flood deposits with quartzites and wood chips and all that, all the kind of things you'd imagine. And so I'm now working with paleoclimate people. We're both working on the same exact cores in the same spot. I'm doing the earthquake part, they're doing the climate part. And that's something we couldn't do before. And I would have bet a lot of money that that wouldn't be ever possible. To get a climate record out of a subduction zone. But it is possible, it turns out. This is Mo Walczak that's working on this. And turns out it is possible. And yeah, the Missoula floods are definitely there.
Well, that's very exciting. And I bet that question, I don't know if it came from Cheryl or Ralph. Ralph is our newest advisor for QGS. So thanks, Ralph and Cheryl. And thank you again, Chris. We're just under 2 hours. Sorry about this, everybody. And thank you for everybody attending and staying in there. I mean, it's really great information, and thank you again.
Well, thanks everyone, and thanks.
I think it's probably. Go ahead, Chris.
I was just going to say thanks everyone for. I'm not the fastest speaker in the world. I know some of the stuff was probably a bit too technical for some folks, maybe not quite enough, but I was trying to fit that in. But anyway, thanks for the invitation. It was great fun.
Yes. Well, everyone take care. And our next presentation will be March 18th, and that's David Williams. And Chris, good luck with your trip. Hope you and your wife are safe, and have a good margarita for me.
We're gonna go do that right now. Thank you.
And pet your kitties for me.
What was that?
Pet your kitties for me.
Oh, thanks. Who is that?
Do you have cats on
Tim.
that boat?
Yeah, we have two.
Do you have a cat on that boat?
Yeah, we have two.
Take care. Bye.
All right.
Okay. Take care.
Bye-bye.
Bye.